All right. So I was telling you in-person people, I'll tell you online person people. So our projector lamp went out, so we called the tech people. So hopefully we'll have one. And anyways, I'll have to work around it, which was poor timing because there's a lot of pictures I wanted to show you here today. So maybe I'll just hold up the textbook, or maybe it'll be back here and we can get started nonetheless here, especially if we get to doing some questions here. So like I said, keep our fingers crossed. Maybe we'll get a lamp real quick, or maybe we'll take a break early and we'll have an earlier break and then a longer second half, or something to that effect. So with that in mind, let's go ahead and jump in then to the material. I wanted to take a few minutes, and I still will, take a few minutes and give you some information about the exam and the homework, and I bet you're very curious about that. And that's what I planned on doing first, and I plan to do that by showing you the Canvas page through the projector. So with that said, I'm still going to do that, and I'm sure you still got questions. Let's just do that a little bit later, because again, I want to get that stuff on a video, and I want to use the projector for that. So with that in mind, I'm going to shift from what was going to be the first 10 minutes talking about the test and what to expect on the test to let's jump into this next chapter here. All right. So with that in mind, I would kind of describe this for chapter 4. Chapter 4, I would call it dynamics. I would use the phrase explain motion. In other words, these last two chapters, first on one-dimensional kinematics and then on two-dimensional kinematics, really, in my definition, would go under describing motion. We did not really explain why the falling object had an acceleration of 9.8. We did a lab on it where we measured it and we did a bunch of calculations why it was 9.8, but we didn't explain why it was 9.8. We just said if it is 9.8, then it would do blah, 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 blah. I would put that in picture form like this. For us to get the position, the XY position of something, we got that from the velocity. And I'm going to put like a little double arrowhead here. And then I'm going to put acceleration here with another double arrowhead. And I would say this is just kind of a slight modification of the diagram you guys saw where I had the derivative of position is velocity, or the antiderivative of velocity gives you position. And so I'm just going to drop that out of my diagram, and I want you to remember it's still there. This is how you go back and forth. And so without really adding to this diagram how you go back and forth, you know that if you know position, you can get velocity by taking its derivative, or if you know velocity, you can take the antiderivative and get its position. Which of course is what we did, and we got those 5 kinematic equations. And so we went back and forth. And I'm going to say the same thing here with the acceleration. Come on in here. Yeah. All right. And so I'm going to say the same thing with our acceleration. That if I took the derivative of velocity, I would get acceleration, or if I took the antiderivative of acceleration, I'd get velocity. And again, that was part of our kinematics equations. So here's the next step. The next step is the dynamics. This chapter and the next chapter and the next chapter are really kind of all the same. They are, how do you get the acceleration? I mean, once you get the acceleration, you can get velocity and position, but how do you get the acceleration? What causes the acceleration? What is the cause of it? And what we're going to see is the idea of a force, a net force. And that deserves some explanation too. What do you mean by a net force? Well, as you will soon see, the net force is the combination. I'm going to use a symbol from your math class. It might have been a while. But have you guys seen the capital sigma, meaning add up a bunch of things? Okay, good. You guys are shaking your heads. And so if you have a force 1, and then a force 2, and then a force 3, and let's just say you have n forces, what we're going to do is add up those forces. The combination of all those forces is saying, what are all these forces equivalent to? What one force are all the individual forces equivalent to? So that is our big step. And so I like to kind of circle this and say this right here. Oh, do I hear? Oh, hey, I hear our technician. Awesome. All right. I'll keep going, but our hero's here. Almost. All right, thank you. I'll see which kind of bulb it is. Yeah.
So just to make sure, the sigma to the force.
Yeah.
So if you have enough force, you can't. I mean, I guess it's not relevant, is it? So that's a one-way arrow.
Oh yeah, good point. And maybe I should put a two-way arrow here, but yes, a one-way arrow here, because when you take a bunch of individual ones and add them up, you get the total. But there are many ways to get that same total. It would be like saying, 3 plus 4 is 7, but so is 2 plus 5. So if all I give you is 7, you don't know if it was 3 plus 4 or 5 plus 2. Yeah, so good point and good catch that this is a one-way arrow, but this is not. So I'm going to put here then chapters 4, 5, and 6. So 4, 5, and 6 are what we're about to do here. And that's most of this week. Hopefully we'll even get to 7 after the exam on Wednesday here. And that hopefully then ties together with what we did in chapters 1, 2, and 3. And so that's how I want to begin this chapter, is kind of give you the big picture of, where are we, where have we been, where are we headed, and I think that will help, because I can't overemphasize this enough, and I think you guys are starting to catch on, but it's going to take, I think, a little while for it to really sink in. Physics is different than a lot of other classes. Physics is about knowing how a few fundamental and powerful ideas explain a universe of phenomena. And so I'm going to joke with you. Would you like to know the homework? Would you like to know the answer to all the homework for chapter 4? How about chapter 5? How about chapter 6? Here it is, right here. I can guarantee that. This is what's going to happen. What's going to happen is you're going to look at the problem and have a bunch of forces. You're going to combine them together to get the net force. The net force is going to give you the acceleration, and from the acceleration, you'll figure out how fast it's going, and then from how fast it's going, you'll figure out what its position is. There it is. That's what we're going to do. Now, I admit that may sound really simple. Because in terms of memorizing stuff, it really is that simple. In terms of logic and the deductive reasoning and working through the problems, they're all unique. They're all different. They're all going to tax your brain into solving this puzzle, and that's what I want to keep emphasizing here. All right, so here is the good news about forces. Let's just kind of give what I'll call a layman's definition of a force. Nothing fancy here, no big scientific words, something that is kind of just useful for us to get started. And I'm just going to say, what is a force? A force is any kind of push or any kind of pull. So, if somebody puts their hand on your shoulder and they push you, that's a force. Somebody kicks you, or I have to go the other way. You kick somebody. You put a force on them. If there's a rope, a stick, basically, all these things I'm talking about are what we call contact forces. There's some kind of interaction because of the molecules that are in the human hand or in the stick or in the metal rod. There is this push or this pull. Now, to be a little more honest and to dive a little bit deeper, but we're going to do that next semester. For those of you who are hanging around next semester, we'll see that this interaction of molecules is really an electrical force. And so that's kind of a deeper dive. But we got to build up to that. So we're just going to take a layman's definition and says anything that pushes or pulls. Now, I would say there is one very important exception to that, and that is gravity. I mean, if I just take this little marker and let it go, as we've been doing in the last chapters, the Earth is pulling down on it. We would say then it has and we're going to use a common word, weight. That's going to be the force. The force of gravity pulling it down is its weight, which results in an acceleration, which that part we've already been studying, right? That part's already the 9.8. We already know it has an acceleration. But what we haven't done is said, why does it have this acceleration? Come on in, either way. You're the prime guy today. You must have a rewarding job when you come in and you're the hero of everything. Yeah, we're putting a lot of pressure on you. Okay, but while he's doing that, I'll keep talking here, and I'll kind of stay on this half of the room here. So what I'm trying to say is probably the only force here at the beginning that isn't a contact is the force of gravity, what we'll call the weight. All right. So again, it's a push, it's a pull, and then I should probably say, like any new quantities, we would have some units. Well, you saw this pattern already beginning, right? You saw the pattern where we said, what is position, and we measured in meters, and then what is velocity, meters per second. We did area, square meters, and now we're going to say, okay, what units would we use? Well, we use the unit, a Newton. And so we'll say something has a force. So if you push something and go, oh, that's 10 newtons, or maybe a real hard force. Oh, that's 100 newtons. And so we'll have things that look like this. We'll say the force is 100 newtons. Okay? And so we'll use that capital N to represent a newton. Now, maybe jumping ahead, but you're going to see this when we talk about Newton's laws of motion. A newton is equivalent to the unit of a kilogram times a meter over a second squared. And I'll prove that to you as we get a little deeper into this chapter, but I just want to start that as we start to do our calculations, right, we got to be careful with our unit analysis. And so we need to know what makes up a newton. You might remember when we did chapter 1, I said every unit we introduce here throughout this semester is going to be a combination of kilograms, meters, and seconds. Everything's just going to build up. And this is kind of where we are now. We're going to build up. And you're going to see that in not every chapter, because not every chapter we get a new unit, but every time we get a new unit, we'll come back and say, okay, what is the new unit to measure this new quantity, newtons, and then what is it made out of in terms of the base units, the kilogram, the meter, the second squared. So maybe just to put some names here, let me put some names for some forces. Tension is a good one. Compression / normal is another good one. One I also just mentioned, weight, or what we might call the force of gravity. And maybe that's worth pausing, saying there's the force of gravity, and then there is the acceleration that is caused by the force of gravity. And I want to keep emphasizing that because I know that the beginning student often can pause and say, well, didn't we do the force of gravity? Isn't that 9.8? And it's like, no, right? Well, back to the chart. The force of gravity, the weight of it, then determines the acceleration of 9.8. So don't confuse the result of the force of gravity with the acceleration of gravity. All right, well, more to follow. Another one I want to kind of introduce you to is frictional force. I guess air resistance. In fact, maybe I'll put those kind of together here because what we really call friction when two solid objects rub against each other. But when you have a solid object moving through the air, the rubbing is still molecules rubbing, so they're a lot the same. But in this case, I would say that the rubbing is between a fluid, the air, and the solid. And so we're going to see in chapter 5 that that's going to make a little bit of a difference here. Oh, hey, that's looking real nice. Thank you. All right. All right. And I'll come back to that and work that in. But let's since we got started here, let me keep going with where we are, because what I want to do then is to point out then that in this diagram here, and in fact I'm going to have to now erase the diagram, but keep this picture in mind, that what I'm trying to get you to see here in this chapter, in fact it's chapters 4, 5, and 6, that we're going to look at a bunch of forces. And of course from that look at the net force, which then determines the acceleration. So we have to do this beginning part by talking about a bunch of forces. And there are more forces than I labeled over here, but obviously we got to start somewhere. And this little short list I made is a really good starting point. So here in chapter 4, these are the forces we will be left with. Now, let me then kind of illustrate or point out each of these. And a tension, which is why I brought this cotton string here, is really just a fancy word for a pull. And so if I take this cotton string, and you can see it's not a very strong string. Let me just lasso something. How about this little metal piece here? I'll tighten it up. But if I use this string or rope or cable or chain and I pull on something, I would say I'm applying a force. Specifically, it is a tensional force. Now, a compression would be what happens if I were to push. Now, you can see that for a string, that's not going to happen. So anything that's flexible, a string, a rope, a cable, a chain, you can pull on it, and so you can have tension, but you can't push with it, so you can't have compression. And obviously, if you pull too much tension, there's some point where the chain or the rope or the cable will break. So there is a maximum amount of tension. But if you hear me use this word, hey, we're going to apply some tension, that's what it means. It means you're yanking on it, you're pulling on it. It's also why I brought this metal rod here with this C-clamp. I can hook it on here, and with it I can pull. Now, obviously I can't pull until this one breaks, but I would say the same thing, that this metal is under tension. It's applying a force. But the reason I have this one is then I can push with it also. And I can push inward. And that way I'm compressing the molecules. And so in that case, I'd call it a compression force. But nonetheless, it is still a force. That's what you really need to know. Is it just one of the many forces that we're going to have to put together to figure out what the net force is, which is what we need to then figure out what the acceleration is. And that's what I'm trying to illustrate. But obviously we have to understand the words, because if we don't understand the words, then when you read the question, you're like, oh, what do I do? So if you ever see compression or you see tension, hopefully it'll make sense to you. Nothing fancy, it's just a push or a pull. Now, with that in mind, let me take this off and say, what about something that is kind of heavy that then sits on this desktop, and so it compresses the desktop? Or you might say that the desktop is pushing upward on it. I mean, you know what would happen if I didn't have the desktop? It falls. And so what I'm trying to say is there is a push. There's an upward push from this desktop. I would call that a kind of compressional force. But when it's pushing against a flat surface like that, we like to use a fancy word from our math class. I don't know if you guys have ever seen this from your math class. Do you know what a normal is? So a normal is a line that is perpendicular to a surface. So if a line would be represented by this metal rod, and this desk is a surface, then this is the normal. This is perpendicular to the surface. And so this surface, because of the molecules that are in there, are pushing back. Now again, this is where we just have to kind of brush over how complex this can be with all the molecules. We just want to, at this point, say there is a force pushing back. There is a compression. Let's call that a normal force. Now, if I take the side of this table, normal to it would be a line coming out this way. So if I said there was a normal force from this surface, what I mean is it's perpendicular to the surface. If it was this surface over here, well, then it would be normal would be in this direction. And so we're going to need to start thinking in 3 dimensions here, because we're going to have 3-dimensional objects. And the normal to this surface is up, and the normal to this surface is left, and the normal to this surface is out. But again, if you kind of hear me say that, hey, there's going to be a normal force, well, I'm talking about, you know, the surface of some material that's being compressed and it's pushing back. And so that's what this normal force is. Now, we're going to study the weight and the force of gravity a little bit more a little bit later, but for now, let's just say, look, you can kind of see it, right? It gets pulled down. If you've ever tried to pick up a big boulder or a bag of cement or even just a bunch of groceries from Costco, because they give you those giant bag things, you know that there is this pull down, right? This force of gravity. And so that's a weight. That's the one I said is the only one that we're going to spend a little time and say, don't forget that one. Because the other ones are easy to spot because I can just say everything that's in contact. So if I have 3 ropes tied to it, I go, well, there's going to be 3 forces. Plus gravity, the one non-contact one. And so when I say add up all the forces, you got to make sure you recognize all those forces. And that's what I'm trying to get here at the beginning. You got to recognize, hey, there are a bunch of forces here. How many? You don't want to miss any. Or you don't want to make any up. You'll get the problem wrong if you make them up or if you miss one. And so you got to recognize how many things are contact plus gravity. Now, friction and air resistance, I guess I would describe also as molecules hitting. Where did this block go? And so if I come over here, I would say that as I push it along, there's rubbing. There's rubbing between these molecules and these on the surface. In fact, if I tried to draw a picture of this, it might look something like this, that here is the block of wood, and if I were to magnify the bottom of the block of wood, I would see that it has a bunch of unevenness with it. And then likewise, here's the table that it sits on. And again, if I were to magnify the surface, I would see that it is not completely smooth. It's got some rough edges. And so again, without too much depth here, but enough to get us started, I would say if you try to push this along, then these things would bump into each other. And so if I used my hand here to say I'm going to put a force from my hand And so you might call that a little bit of a compressional force. I'm pushing with the skin and the bone of my hand, and I'm pushing it that way. I would say this bumping and this rubbing here would make a friction. And notice the direction I put. Did you notice it wasn't perpendicular to the surface? See, perpendicular to the surface, this is what I was commenting earlier. And so this table is actually doing two things. This table is being compressed, and so it does have the normal force that I talked about a few moments ago. But as I try to slide it around on the ground here, or the top of the table, there is the rubbing of those pieces, and that would be a frictional force. And in Chapter 5, we're going to take a deeper dive into these frictional forces. But for now, I'll just say there is one, and then that'll get us through this chapter, and then we'll dive a little deeper into that in Chapter 5. And for that matter, also in Chapter 5, we're going to dive deeper into some air resistance. But I would say the same thing, that if I had this block and I hold it up and I drop it, so as it is falling, isn't it hitting the molecules of the air? And so I would call that an air resistance. You might even just call it friction, although again, we like to say the friction is like when two solid things are rubbing each other, and then the air resistance, or sometimes even just called the drag resistance, maybe I should put that. But the drag through the fluid is when the solid object is bumping into the fluid pieces. So again, trying to build up to how we're going to get from these individual forces to the net force to the acceleration. Keep that in mind. That's the big picture. But of course, what we have to get started with is, okay, what forces do we have to work with? And I'll say it again, there are more than this, but this is what I call our first four. These are our first four to kind of get us started, and just to try to give you a feeling for how to work with this. And it's going to take us 4 chapters to really digest this. And so the famous person in this whole discussion, I'm sure you heard of Newton. You already heard me say that the units of force are measured in newtons. That's to give honor to Newton. And Newton has 3 laws. There are 3 laws of motion. And in my own silly way again, I'm going to say, do you want to know the answers to all the homework problems in chapters 4, 5, and 6? It's right here. It's these next 3 sentences that I'm going to give you. If you can learn Newton's 3 laws, you can describe any motion. And that's why I keep saying physics is about knowing how to apply a few powerful, fundamental concepts to explain a universal phenomenon. And so whether we're talking about a bus that's moving, or a train, or a rocket ship, or a molecule, or a bacterium, doesn't matter. I can guarantee that I can explain its motion with these 3 sentences. And so let's introduce them to you now. So we start off, and I'm so glad they got the projector running, because this is where I wanted to save a little bit of time and not have to write them out, but to then be able to show them to you in terms of your author. The first one is probably the simplest one. I don't want to say it's the least important, but it's almost so obvious that sometimes we even forget that we're using it, But I do want to overly emphasize that we use it all the time. And I must have passed it. Ah, there it is. I'm going to make that a little bigger on the screen. What if I go 125%? But we often refer to it as the law of inertia. It just simply says that a body at rest remains at rest. Or, if it is in motion, it remains in motion with a constant velocity. Notice it didn't say speed, constant velocity. Unless acted upon by a net external force. So let's look at these last three words first. Particularly this one, I think we've covered pretty good so far. Force. What is a force? So I'll say it again. A force is any push or pull. Let's just limit our discussion for right now to these four. Okay. And so any kind of tension or compression, also normal, any kind of friction, any kind of weight, okay, all of those are a force. But the concept here is very important on this word external. Ooh, let me talk about external. So let me take this wood block again and say, I want to know about the motion of this wood block. And what I'm trying to say here is the forces that are applied to this wood block ultimately determine its acceleration, which then determine its velocity, which then determines its position. And so I need to look at these forces, but I'm going to say it has only external ones. In other words, if you looked at the molecules that were in this piece of wood, maybe there is one atom here and another atom here, and maybe atom 1 pulls on atom 2, and atom 2 then does something to atom 3, but it also maybe pulls back on atom 1. None of that's important about the motion of this. And that'll make more sense when we get into Newton's third law. You'll see that all of the internal forces cancel off and do not contribute to the motion. So if we want to know the motion of this, it's what somebody on the outside pushes it. Or if gravity pulls it down. And so the good news here is we don't have to take a deeper dive into the internal structure of our boat or our plane. We just need to know the external one. So if it's a plane, how is the air affecting the plane? Not what is the pilot doing on the inside. Is the pilot pushing on the dash? Somebody in a car, if it breaks down, never sits in the driver's seat and pushes on the steering wheel and said, I got to move this car out of traffic. It broke down. No. You get out of the car and push the car. The motion and the behavior of the car is only influenced by external stuff. So that's good. That's going to keep our thoughts a lot easier because we only have to worry about the external ones. And then also, here is what they say, the net. And here's why. To try to give you a feel for net forces, let me start drawing some pictures. Let me even use a fancy word. We're going to call this a free body diagram. In other words, what if I were to take this object and push it with a force of 3 newtons to the right, but somebody else pushes it with a force of 3 newtons to the left? All right. So what do you think if somebody pushes with 3 this way and somebody goes 3 that way? Yeah, doesn't that seem like it would be the equivalent of nobody pushing it? Right? And this is what we mean by net force. This is what I had in that diagram, where take all your forces and combine them together. And notice I said combine, not necessarily add, because in this case they're opposite. So you might do something like this. You might say, okay, here's what I have. I have in the x direction, I have force number 1, and I will add it to force number 2. And in the y direction, I don't have any forces. In this first one, I might call a positive 3 newtons, and this one here, I'd call a negative 3 newtons, and so the total of that is 0. And so the best way I know how to kind of get across to students about net force is to say, look, combine all the forces together and get what that's equivalent to. And we've already been doing that quite a bit. Isn't that why we learned about vectors? And you're probably still kind of struggling along with those. But we've been doing problems in this last chapter where we said if you threw an object up at 5 at an angle of 37, you would say, well, don't think of that as one force, force. Don't think of it as one velocity, but think of it as a horizontal velocity of 4 and a vertical velocity of 3, and the combination of the 4 and the 3 make the 5. And so we could take 1 and combine it into 2, and I'm going to ask the other way around. Can you take the 2 and combine it into the 1? And that's what I'm saying here. That forces then are a vector. And so when I say combine them together, I got to put x's with x's and y's with y's. And so if I have a bunch of forces, to get the total result of those forces, I've got to add them together like vectors. Do you remember in the last lecture, or maybe it was 2 lectures ago, where I stood here and I said, I'm going to turn 20 degrees and go 11 steps, and then I'm going to turn 70 degrees and go 5 steps, and I'm going to get the total of those 2? I'm going to be asking the same thing of you. And so we're going to be adding those forces together to get what is the net force. Yeah.
I hope this makes sense, but you know how we have to be mindful about the negative values for things like 9.8 and stuff like that? Would we do the absolute value for the external forces?
No, we'll do positive and negative, and that's why this one I did a -3 for this one.
Mm-hmm. But for the answer, like if for the net external force, would it always have to be positive?
No, it could be negative. In fact, I would probably prefer if it comes out to be negative, that you list it as negative, because that would indicate the combination of those 2 forces is left, whereas a positive would be right. In fact, I'm glad you said exactly those words, because this is the next example I want to give. Let's do this for net force. What if I took that same block and I push to the right with 4 newtons, and somebody over here pushes to the left with 3? And compare that to, what if I only push with 3 to the right, but somebody else pushes to the left with 4? So if I come back to this one, I might say this, that the net force in the x direction was 0. And I haven't really dealt with the y direction purposely yet, because just one dimension at a time is hard enough. But the net force in the y is also 0. And so here I would say this is an example of something that has a net force of 0. And notice that net force of 0 does not mean no forces. And notice that according to Newton's first law, this is what we care about, the net force. What is the combination of all the forces? Once you can put them all together, what do you get? So you guys did a good job over here, so help me out here. What would you say the net force is in this case? Yeah, 1 Newton. And a positive 1 Newton, right? So I would say positive 1 Newton. You might even say that's the x direction, because I really haven't even said anything about the y direction. But what would you say here is the net force in the x direction for a scenario like this? Yeah, and so again, I'm going to use the word combine all the forces together. Maybe now it's worth putting this back up here. So if I combine all the forces together, I'm going to get the net force. And I'll even say that although I've been showing you in the x direction, I hope you're seeing that we're going to do the y direction also. And of course, then it's this net force that's going to give us the acceleration. It's these steps that I'm trying to illustrate here today. Let's try a harder one. What if I push with 3 newtons to the right and somebody else pushes 4 newtons up? What's the net force there? Good. It's tempting. I heard somebody say 7, and I know that's tempting. No, these have direction. It's not just a simple 3 and a 4. In fact, I probably should put that one here, that if I pushed with a 3 and somebody right next to me pushed in the same direction with 4, I would say those two are equivalent to 7. And so instead of thinking of it as 2 individual forces, I would say, hey, that's just one big force of 7.
Is that going to be 5?
Okay, yeah, so this one coming back here, good. You're beginning to see it. This would be equivalent of 5. Or you could leave it in its components. So I'm going to do both, right? You could leave it alone and say, all right, let's just look at x and y by itself. And if you did that, you would then say, well, the net force in the x direction would only be 3 newtons because the other force doesn't have anything in the x direction. And so when I say combine all the forces, I mean put x's with x's and y's with y's. And so I only have a 3 in the x, so that's the total net force in the x direction. And in the y direction, I would have a net force of 4 newtons. Right. On the other hand, if you wanted them to think of them as one big force and say, what is the magnitude of that? You get the idea that we've been doing. Good. We can put these together like a vector. And if you had a 3 newtons to the right and a 4 newtons, the net would be 5 in terms of magnitude. Right? And so this would be that famous 37 and 53 degree angle if we bothered to get out our calculator and do the inverse tangent. And I'm pretty sure you guys could do that if you were to ask. So if it just said what's its magnitude, that's what you would do. So you're seeing here that when I keep saying right here, combine all the forces together, what I mean is they are vectors. Put x's with x's and y's with y's. And in some problems, we'll leave them separately so we can then get the acceleration in the x and the acceleration in the y. Other problems, we'll combine them together to get the magnitude. And so we're back to working with vectors and saying, look, that's what it's equivalent to. How do you want to view it? Well, I think I probably have said enough then to make Newton's first law make more sense. Basically, it's saying this. If there is 0 net force, it'll remain the way it is. In other words, if it's at rest, it will remain at rest. But if it's in motion, it will remain in motion. I like to say Newton's first law really is saying whether there will or will not be an acceleration. And so if the net force is 0, you're going to say no acceleration. And I want to emphasize, no acceleration doesn't mean stay at rest. Did you catch that? No acceleration means do not change your speed. So if you're already moving, you're going to continue to move if there's no acceleration. I brought a couple of examples out here to kind of illustrate this. So looking at a case like this, oh, I have since erased it. Let me put it back on the board. But looking at a case that has 3 newtons on each side, you guys already told me, 3 newtons on each side would get a net force of 0. That would tell me no acceleration. And so I just want to say right here, there'd be no acceleration. But all these other ones would have an acceleration. See how there is a net force? This one even has a net force. Oh, I guess I didn't write it down. -1 newtons. This one has a net force. This one has a net force. So all of these, I would say, accelerates. So that means they change their speed. So that means if they were at rest, they're going to start moving. If they were already moving, well, depending on direction, they maybe go faster or slower, or maybe even turn. Ooh, turn. Well, let's wait until chapter 6 before we get too detailed into how much force and what direction makes it turn. But that's where we're headed with all of this. And so I brought off or out a couple of kind of fun, hopefully fun, little illustrations. Here's Newton's first law, a good one in action. I'll come over here and I'll do it twice, so I'll turn it towards you. I've got 2 of these purposely so you can kind of see the interaction here, but I've got a pretty heavy weight. And so I would say right now it's not accelerating, right? I can just look at it. It's at rest and it's staying at rest. That means Newton's first law is saying the net force is 0. And that kind of makes sense. I know gravity's pulling it down, but then this string up here, tension, is pulling it up. So if those two were equal and opposite, kind of like those 3 and the 3, then the net force here would be 0. My question for you here is, if I take this bottom string and I pull until something breaks, will the top one break or the bottom one break? And most people at first say the top until I do something like that. And then they tell me, oh, so the bottom one breaks. I said, well, you want to take a bet? Because I could pull it until the top one breaks. Why the difference? And this is a really good illustration of what we call the law of inertia. These things have, and the fancy word is inertia. Let me just say mass. They have mass. They're at rest. They want to remain at rest. So when I go and tug on it, that wants to move the weight. But there is a delay, if you will. There's a sluggishness to it. There's a resistance to it. There is this thing called inertia, which we measure in terms of mass. And so if I do a quick jerk, I don't give it time for this to move, and the tension down here never translates up here. So which one breaks when I do a quick jerk? The bottom one. But on the other hand, and I think this is what your gut was telling you when all of you said the top one was going to break, is you were saying, well, if he's pulling down here, that top string has to support not only his tug, but also the weight of this one. And you're right, as long as I give it a time to react, as long as I let the inertia move and give it a chance. And so that's why down here I was just increasing, and sure enough, the top one broke. And so it's fun little bar trick if you want to make a few bucks with your friends. Oh, no. Don't take money from your friends. Strangers, there you go. But it does illustrate the law of inertia. And I bet a lot of you do this on a regular basis, not thinking too much about it. I know I do all the time. When it seems like I'm getting a paper towel out of my kitchen, I end up going, okay, chicken's in the microwave. It comes out. I grab the plates. Roll of paper towels are over here. I got one hand occupied. How do I get one sheet off of that paper towel with one hand? And I first pull it real slow so it unwinds. I give it a chance to unwind. But I take advantage of the inertia that's on that roll, and then when that one sheet gets all the way off, I pull it real quick. And that makes the tension tear right at the perforations, taking advantage of the inertia. And it works really well when the roll is new because there's a lot of mass or a lot of inertia to that roll. It's when I get down to the bottom and there's like 7 sheets left on there. I was like, okay, if I pull it quickly, there's not much inertia there. And because of that, I can't really take advantage of the law of inertia. And sometimes it works, most of the time it doesn't. It just unwinds the other 7 sheets, and I end up with 7 sheets here. And so that's the law of inertia. So I thought that'd be a fun one to see. Here's another fun one to see. And I better kind of move along here so we can get into some of the numbers here. But I have a plate, I have a fork, I have a glass. I even have a glass with water in it. And more interesting, I have a tablecloth underneath it. Can I take the tablecloth out from underneath without spilling the water or breaking the dishes? This is another good example of the law of inertia. See, they're at rest and they want to remain at rest. Now, again, I want to emphasize, they don't have to stay at rest, but in order to move, in order to have an acceleration, they must have a net force. And so you have to do some kind of push or pull on those dishes to make them move. Now, that's not really a paper, not really a tablecloth. It is just paper, but it's butcher paper. So it's that smooth butcher paper. And the reason I picked the smooth butcher paper, I guess I've erased it, but it's that friction. It's that rubbing between that plates. And there, fortunately, is a very, very small amount of friction between that smooth butcher paper and that plate and that glass. So, the first law of inertia says if the force is 0, they won't move. And if they're near 0, they'll barely move. And so, 1, 2, 3. I'll just pull it out. And they move just barely, but they stayed there. And so this is an example of things at rest want to remain at rest. They will move with enough force on them. So if I did this, whoosh, they will move. But for the most part, they want to stay there. Now, I think the harder one to kind of visualize is what if they're already in motion? Because remember, if the net force is 0, we're saying they would have no acceleration. And so if I take this puck, I guess it's a soccer puck, and I give it a little push and slide it, you'll see that, of course, my hand gives it a push, so I would say there is a net external force, so it does accelerate what my hand is pushing on it. And once it's going, then what happens? Does it keep going? No. It seemed to have come to a stop. And why? Because there is a net force, and that would be friction. And so this one is designed to have a little blower on it, and it makes kind of a little air pocket underneath it. So once I give it a little motion, now there's no more force. Of course, until it hits something. So it just keeps going with the same velocity. Same speed, same direction. It doesn't need a force to keep going. That's what I want to emphasize. The force gives it an acceleration. And so once it's in motion, it's just going to stay in motion. And so my hand gives it the force to give it some motion. And then once my hand stops pushing on it, the net external force is 0. Therefore, there is motion in a straight line at the same speed forever and ever. And that's what 0 acceleration means. Don't change your velocity. All right, well, that's the first law, and maybe I should then move on to the second law, because like I said, the first law, sometimes we forget about it because it really is that simple. It just tells you whether there is or is not going to be an acceleration. It's the second law that is much more interesting. The second law then tells us, and I'll leave that up here, how much the acceleration is. I like to say this, that the second law picks up where the first law leaves off. So the first law again tells us whether there is or is not an acceleration, but then the second law is an equation. And this is probably where we're going to spend most of our time, with the equation. Once we know that there is or is not an acceleration, we want to find out then if there is, what is its value? Is it 1? Is it 2? Is it 3? What direction it is? Because that determines then the acceleration, which determines the velocity, which determines where it goes. And so this particular equation just simply says this. The net force divided by its mass is equal to its acceleration. This is, and I hate to kind of rank Newton's 3 laws, but I'm going to do it anyways. This is the important one, the most important one. This is the one where we're going to put some numbers together. We're going to put all of our forces together to find that net force. We're going to then divide by the mass, and we're going to get the acceleration. And so that's this piece here. We're going to find all these forces. We're going to make sure we recognize them all. We're going to find out what direction they are. We're going to put them all together to get the net force. Once we get the net force, we're going to divide it by its mass to get its acceleration. Now, I should point out here that I put little arrowheads over here purposely, because if we get net force in the x direction divided by mass, that'll give us the acceleration in the x direction. And if we get net force in the y direction and divide it by its mass, we're going to get acceleration in the y direction. And I'll say it again, once we get the acceleration in the y direction, we can then pick up where we did these last few chapters. From acceleration, we can get velocity, and from velocity, we can get position. So you can see how our learning today is like climbing a ladder. We're going to learn something new, but once we use that new stuff to get acceleration, don't forget the lower stuff on how to take acceleration and make velocity and position out of it. And I must say, most of our problems then stop right here with the idea that you could go on. You already know that. You already learned those in the past chapter. So a few of them will ask you to go all the way to position, but most of them will just say, here's a bunch of forces. From that, what's the net force? And from that, what's the acceleration? And as you pointed out, some of them will go the other way. Here's the acceleration, so give me the net force. However, you might have troubles getting to the net force to the individual forces unless, and I should have said this earlier, if you know there were 2 forces and they gave you one, and you know that one, then you could get that other unknown force. And that's a common question. It would be like saying, okay, the net force is 7, and it's made out of 2 forces. One of them is 5, so the other must be a 2, if they're in the same direction. Yeah. So there are questions that will ask you to go, and maybe I should do this, dot, 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 the other direction. Because you can go the other direction if you know a little bit over here already. If you know all the other ones but one, then you can go that direction. And so you will be asked to go in that direction. And it just dawned on me as I was doing this that, okay, maybe I should expand on your question. Okay, so with that in mind, maybe I'll show you this, but this one I think is relatively obvious, and most people kind of jump on it right away. I like to kind of show it with this little plunger cart here. This plunger cart is nice because I can push in the plunger part way and get a small force. I can push it in a little bit more and get a medium force. Or I can push it in all the way, and this plunger cart has troubles. It's missing the release spring. Hang on, just a second. This isn't going to work well. Let me grab one. All right, I think this one's look better. But here's a good illustration. Let me just put it on the low setting and release it. And most people aren't surprised. They see it move. While the plunger was pushing, there was a force, so it did have an acceleration. The acceleration seemed to be kind of small, and it didn't go very fast. Okay, but if I push it in all the way and release it, well then it goes a lot faster, and that is, of course, because it had a bigger force. The bigger force resulted in a bigger acceleration for that push of the plunger, and then it went across the track, roughly at a constant speed, because this rolls pretty good. There is some friction, but the best we can do is show it without rolling. But this is a good illustration of what I think is pretty obvious to most people, that more force gives you more acceleration. In fact, that's the lab we're going to do today. We're going to ask you to do a couple of different things in the lab, and one of them is to say, keep increasing the force, and you'll keep seeing a bigger and bigger acceleration. And the math says they're proportional, so we'll go into the lab and we'll measure that, and we'll say, okay, if you double the force, you double the acceleration. You triple the force, you triple the acceleration. And so we will see the mathematical connection and verify Newton's second law. Now, the other one, though, that easily gets overlooked, and so let me just illustrate it again, is I'll release it. And I would say that's a pretty good acceleration. And of course, that's because I have a pretty large force. But what if I still have a large force, but I have a lot of inertia? And I'm hoping you can kind of see it in the math here. Since the mass, or the inertia, and that's why I keep calling it the resistance, that's why we call the first law the law of inertia, because it's the resistance to move. The mass plays the role of, hey, it's just hard to move just because there's so many atoms and molecules there. And so when you start making this number bigger, even if you left that high, you end up with a small acceleration. And that's what I hope you'll see here, is Newton's second law in action, where I'm going to give it a large force, but the denominator has a large mass. And so when I do this, I don't get much acceleration. All right, well, that's Newton's second law. And then finally the third law, and I'll say it again, if you can kind of memorize these three laws, first, second, and third law, this is what we're going to put together for every problem in order to solve it for chapters 4, for chapters 5, and chapter 6. And hopefully by the time we get to chapter 6, you're going to be starting to look at that, hopefully like you did on the homework, where by the time you were getting to that last projectile motion, you're like, oh yeah, this is just the same thing over again. And if you weren't there, maybe I should encourage you, you should probably do some more problems, because they should begin to look the same to you. It should be just the same thing over and over. I make an X and Y column. I look at the motion in the X. I look at the motion in the Y. You know, they give me some information. Every problem gives me different information, so I got to use my deductive reasoning, but the basic idea is the same between motion of the kinematics for the last problem and the motion for the kinematics on this problem and the motion for the kinematics on the test. That's really was the purpose of doing so many homework problems. So you can get to the point that you're looking at it and going, oh, yeah, this is same thing. I can do this one. And so when you do that on the test, you go, oh, yeah, this is the same thing. Right? You don't want to be struggling during the test, going, oh, now how do I do this? I know I can look at my notes. Okay, so how do I do this? Because you'll run out of time. You want to be able to say, okay, I know how to do a problem like this. I've done a bunch of them. And this is just the same thing, except last time it was a motorcycle going over a bunch of buses. And this time it's baseball going to the outfield, you know, or whatever, just some other projectile motion. All right, well, on to Newton's third law. And so the third law is actually a little different than 1 and 2. See, 1 and 2, as I'll say again, I think 1 and 2 tie together. 1 and 2 are talking about the same object. 1 and 2, the first one says, is there or is there not an acceleration? And then the second one gives me a formula to calculate that acceleration. But the third law, which is often referred to as the action and reaction, involves two different objects. So let me call this object 1 and object 2. And it simply says this, that if object 1 is pulling on object 2, so let me put like a little arrowhead right here. Oh, let me even write it this way. This right here would be the force, and I'm going to put on number 2, and it is from number 1. And those prepositions are going to be extremely important, because the action-reaction is saying this, that number 1 is then putting an action on this. It is pulling on this one. But then number 2 is then pulling on number 1. And those are equal in magnitude, but opposite in direction. And why that makes it important here is when we start working with an interaction, as we look at this, we can then only have to know one of these two, and then we know the other one. Right? They are the action and reaction. Earlier, I said, when we talked about Newton's first law, that if I had molecule 1 and molecule 2, I didn't need to worry about them if they were internal. And this explains why. Because according to Newton's second law, you add up all the forces to determine the acceleration. And if the forces are internal, you would add up both of them. Both of them would be on that object. So you're always going to get a net of 0 from anything that's on the inside. Again, if your car breaks down, and so your car breaks down and you go to push it and you don't get out of the driver's seat, if you push on the steering wheel, then the steering wheel pushes back on you, which results on you pushing on the back of the seats. So you end up canceling off your effort because you're internal. But if you're outside the car, then you push on the car, which of course now the car pushes back on you, which then makes you kind of go backwards unless you put a force on the ground here, but again, that's on the ground. That's not back on the car. So the car only has one force on it, so that's why the car will now accelerate. So only external forces would make motion. Internal ones would not. And this is that reason why. And we could take advantage of it. A good example is what we call a rocket car. How does a rocket work? This is my makeshift rocket. Imagine this is my fuel. But it illustrates Newton's third law really well, because if I release this pen and all of these get pushed that way, so there's a force to, I guess it's my right, your left, as it goes that way, then there would be an equal and opposite the other direction. So this little ramp is going to push them this way, and then the fuel, these little ball bearings, are going to be pushing the cart that way. They're going to be equal and opposite. And so the little ball bearings will go that way, and the cart will go that way. And so this is kind of the simple design of a rocket engine. Just send something that way. And it's no different than, say, paddling a canoe, a kayak. You push the water that way. So I put a force on the water back. What does the water do? Puts a force on me the other direction. So I take advantage of Newton's third law when I'm paddling the kayak. The airplane with the propeller does the same thing. The propeller comes around and it has this little curve to it, so it catches the air and pushes it back. So it puts a force on the air back. So if there's a force on the air back, what's the opposite? Then there's a force on the propeller, which is connected to the plane, in that direction. When I walk, I do the same thing. I want to go that direction, so I take my leg and I push, interesting enough, which way? Does my leg push that way? No, my leg pushes the ground that way. So I put a force on the ground that way. So what does the ground do? Puts a force, equal and opposite, pushes then me that way. That's what I need. To go that way, I need a force on me that way. And what's making me move is not my leg. I push on the ground, so the ground will push back. What's pushing on me is the ground. It's not my leg. I take advantage of Newton's third law. And of course, if you've ever tried to do this on a rug that doesn't have good traction and it kind of bunches up on you, you'll see it. You'll do this, and the rug just goes because you're pushing the rug that way, and it didn't then make you go forward. Or if you were on sand, the same thing. And so you hopefully have good traction there, and you push on the ground that way, so the ground will push you this way, equal and opposite. All right, well, I've said it a bunch of times. Maybe we should look at some pictures, and then it'll be a good time for our break, and come back and do some examples and talk a little bit about the exam here. But I thought picture 5 was a good one to kind of get started. Because even though I've been saying over and over again, trying to make it sound simple, it doesn't always come out simple the first time students do this. I'm sure you're aware of that. But here's what we need to do. Step 1 is we need to figure out what forces they are so that we can then add them together. And so you'll hear me say that to attack these problems, I'm going to give you 4 steps. The first one is to get a good physical picture of what's going on. And the second one is to do a free body diagram. then the math starts. So let me hold off on the next two, but the first two I want to illustrate here before the break. I want to say, okay, this one actually already has a picture. But imagine you didn't have a picture. Maybe you just opened up the textbook and it says, hey, 3 kids are playing. The 2 older girls are going to push the younger boy in a wagon. All right, so you're like, okay, do I got a good picture of this? And I would encourage you to doodle, and this would be my doodle. I'd say, okay, so I've got a kid in a wagon, and the 2 older girls are now pushing the boy who's in the wagon. All right, so there's my physical picture, step 1. Now, step 2, I need to find the forces. Here's where it gets pretty complicated. The forces on what? This is where the third law and the second law can be a bit challenging for the beginning students. When you say the net force and you add up all the forces to get the acceleration, I want to emphasize that would be all the forces on that object. For example, if I look out there and I see a car and I go, okay, I want to know the acceleration of that car. Then I need to look at all the forces on that car. Does it make any sense to talk about the forces on that truck when I'm trying to get the motion of that car? But are there forces on that truck? Oh, absolutely. And I would care about those forces of the truck if I was trying to get the motion of that truck. But so here's going to be your challenge. The forces are on what object? Because when you add them together, you only want to add the forces on that object. See if this illustrates here. All right, so this is why your first step needs to be, what's my object? What am I trying to figure out? So in this problem, it would probably be the boy and the wagon together as your object. And not the girls, not the ground, and if this is on a playground, there might be other kids around. Those aren't important. My system is the boy and the wagon together. And I'm interested in the forces on that object. So, in this picture, you will see that they show force number 1 from the girl that's closest to us, and force number 2 from the girl that's a little further away. Both of those forces are on the boy. They don't even show in this picture. We'll get some harder pictures in just a second. Wouldn't there be an equal and opposite? So if the girl is pushing on the boy, then the boy is pushing on the girl. And so if I came over here and I took this table and I pushed it, I put a force on it, but it also put a force back on me. But if I'm interested in the motion of this table, let me not worry about the forces on me, just what's on the table. And so that's what's illustrated with 1 and 2, and that's what's illustrated in what we call the free body diagram, force 1 and force 2. We're going to add those together. Those are actually on the boy. There might be something else the other direction. Now, those forces alone don't determine the motion of the boy. The motion of the boy is determined by all the forces. So what else is acting on the wagon and the boy? Okay, so we would say weight. Gravity is pulling it down. This would be a good time for me to pause and say, how do we calculate the boy's weight, or the weight of any object? Let me just take kind of an odd object and pretend to just let it go. So the only force on that object is its weight. So maybe this glass, I won't actually drop it, but if I hold it up and I let it go, at that moment, once I let it go, there's no more force from my hand. And if we ignore the air friction, we'll say it's only its weight. So when I say add up all the forces, It's pretty easy to do. It's just the weight. And if I add up all the forces and divide it by its mass, I'm supposed to get its acceleration, right? So if I add up all the forces, which is its weight, if I divide by its mass, I get its acceleration. And in this case, if it's free falling, its acceleration is the g, the 9.8. And so this little equation is going to be very powerful for us. How do I calculate the weight of something? Well, take 9.8 and multiply by the mass, and that'll give you your weight. Oh, by the way, this will be a good time to point out the units. What units do we measure a force, including weight? All forces would be measured in what units? Newtons. And look at the other side of the equation. So when I'm doing units, I'll put it in square brackets. If we measure the mass in kilograms, and the acceleration in meters per second squared, this illustrates what I said an hour ago, that the unit of a Newton is a kilogram times a meter per second squared. All right, well, like I said, after the break we're going to get into the numbers. But right now I just want to do the pictures. So here's our picture. So there'd be this weight pulling down. Oh, what's this N? Okay, normal, that was one of the forces we're talking about, right? And so this wagon is sitting on top, it's pushing down, it's compressing, as we did earlier, so there would be an upward force from the wagon. That's what we call the normal force. Anything else going on? Yeah, good. There is the wagon trying to move, so there's rubbing going on, and so there's friction. So this is why we like to do that free body diagram, because there's a lot going on here. And I would say that there is a total of 5 forces. Did you see them all? Because if you miss them, you can't do the problem correctly. And so in this free body diagram right here, I've got the 2 girls pushing on the boy. We've got the ground pushing up on the boy. We got gravity pulling down on the boy. And we got the rubbing of the tires and the friction there to here. So this is my free body diagram. Because I will tell you, we're going to do math after this. And if we miss any of those forces, we can't do the math right. We've got to have them all there. And this free body diagram is such a powerful step. If you do it well, you'll make the math easy. And that's why you're going to illustrate. This is a powerful, powerful tool. I'll even go the step before that. You can't do the free body diagram real well unless you have a good physical picture of what's going on. And so, of my 4 steps, and I just want to talk about the first 2 here. The first one, get a good physical picture. If you start off with a good physical picture of what's going on, it'll make the next step easier. Notice I didn't say easy, I just said easier. But then you'll get the free body diagram. Because now if you have the free body diagram, the next step is to do the math. And I'll pause and keep looking at some more pictures. But it'll make the math a lot easier if you have a good free body diagram. Oh. All right, let me do a couple more pictures, and we'll take our break here. By the way, I think the author does a good job here in this bottom picture by saying the exact same thing would happen if we replaced the 2 girls with the equivalent of 1 force that is just equal to those 2 forces. And hence, that's why the motion is determined by the net force. It's not how many individual forces you have, it is the net force. It's the combination of all of them. Okay, well, let me go to picture 8, because I think the author did a pretty good job here of saying, hey, let's look at some more forces. This one isn't too much different, so I'll go kind of quickly, but you start off with this rocket car, and then you have to look at all the forces. And in this case, it looks like the rocket has 4 engines, so you get 4 of them. You got weight pointed down, you got normal pushing up, and you got friction. So this one's a lot the same. Let's look at another one here. Here's a good one. Let's say we're focusing on the swimmer, not the wall, not the water, not the people watching her swim, but the swimmer. So we want to know all the forces on the swimmer. And this third law is important because doesn't she put a force on the wall? Because then what does the third law say? The wall puts a force on the swimmer. So when we do our free body diagram, which of these two do we want, or do we want both? Well, the answer is we want the one on the swimmer. So this one here, which is on the wall, we don't want in our free body diagram. We want to know the motion of the swimmer. So we only want to know the forces on the swimmer. So even though she puts a force on the wall, that's irrelevant. We want to know the force on her. Of course, they're equal and opposite, and that's why she pushes to the right on the wall, but the wall then pushes her to the left, and that's why she moves to the left. And so that's where I need to do some examples for you and show you this. This can get tricky. Now, if you really want to see the grand finale, this is where it can get really complicated. And I'm going to illustrate the best thing you need to do is to keep your attention focused on what is it that you're trying to analyze. Because the last diagram, where's the end of this thing? In this book, right here, I would say shows 3 different objects. The person, the scale that the person is on, and the elevator that they're in. And if you start looking at all the forces, you might get yourself confused if you don't quickly at the beginning focus on what is your object. And so the author is trying to say here, let's look at just the person. Because if you look at all the forces, you will see that the scale is pushing up on the person, and so that's this, F sub S. Gravity is pulling down on the person, so those 2 forces are on the person. But notice then, as the scale pushes up on the person pushes down on the scale. So this force is the equal and opposite of that one. Notice then that the scale is being pulled down by gravity, so there's another force being pulled down by gravity. It's the weight of the scale. Notice that the elevator then is also being pulled down by gravity, so there's a weight of the elevator. But then we have here the elevator pushing up on the scale, so there is a normal force. So if the elevator is pushing up on the scale, this normal force here, then the third law says there would be the scale pushing back on the elevator. But do you see how there's a lot of forces there? And do you see which ones are equal and opposite? But do you see the pairs that are equal or opposite are never on the same object? And do you see how it could get really complex if you try to lose your focus on what it is you're trying to analyze? And so make sure you analyze, or you well state in your mind, I only care about the forces on the person. So out of all these forces, which ones are relevant in our free body diagram? Well, only the ones on the person. So it would be the scale pushing up and the weight pulling it down. But what about the elevator? The elevator is not touching the person. The elevator is touching the scale, and the scale is touching the person. But the elevator is not touching the person. And so that's going to be the trick, and it's best to show you by examples. It's okay, now which forces do I need to focus on? All right, well, like always, I talk too much, but hopefully it was helpful. We'll do some examples, but I'll wrap it up and we'll take our break. But I'm saving this one for a break because it kind of makes a big mess here. But you remember the equal and opposite? Do you remember this little rocket car here? I couldn't resist, and I made a better rocket one. And so here's my fun rocket one, because what I have is a lot of compressed carbon dioxide in this fire extinguisher. And as it comes out of this fire extinguisher, it'll come out of this hose and come shooting out of here. And so this situation will put a force on the carbon dioxide molecules in that direction. And so if it puts a force on the molecules that direction, what do the molecules do? Puts a force on the cart that direction. And it's made as a cart, and it's a little funner because I can even ride it. And so if I remove, boy, somebody, oh, there we go. And if I let the air go that way, the equal and opposite will be on me and the cart, with a little bit of friction this way, but hopefully the force that way is greater than the friction, and I will accelerate. 1, 2, 3. And it will push me along here. All right, good time for our break. Let's come back in 15 minutes and get started. So let's call it at about, what is that, 9:55. All right, we'll see you then. Bye. All right. Anyways, let's keep going, and we'll do some example problems. And I was starting to tell you guys that I think that's the best way to see it. We'll probably, again, run out of time, and I'll have to make some videos to send your way. And you can watch as many or as few as that is useful to you. So maybe I should ask for some feedback for you guys. Are those videos helpful? Yeah? Okay, good. Okay. So I'll keep doing that. Sometimes I look and I go, oh, only 2 people watched it. Well, that was a waste of time. But then other times I look a little later and I go, oh, well, looks like 25 watched it. Okay, well, maybe that was worth the time then. Okay. So anyways, let's go ahead and, like I said, grab my calculator, grab my markers. Let's get started. I'll put here number 3 for the first one. And actually, before we start doing the problems, I'm going to put my little diagram up here and say add up all the forces, because that is the net force. And once you get the net force, you can get the acceleration. And then once you get the acceleration, and I won't put the rest of that on there since I think you're getting pretty good at that, and I'm not even sure we'll go that far. All right, so let's see what number 3 says. So this is hopefully an easy one, straightforward. It says a cleaner, so I'll pretend I'm the cleaner, pushes a 4.5 kilogram laundry cart in such a way that the net external force is 60 newtons. So maybe I push more than 60, but there's friction. So maybe I push with 65, but there's a friction of 5. Let's not get too deep. We don't really know. They just said net force. So this one's the easy one. They're starting us right here. And so we know the net force is 60 newtons. And then the problem, and by the way, they gave us the math. It just says calculate the magnitude of the acceleration. So the magnitude of the acceleration would be the magnitude of the net force divided by its mass. So I've got 60 newtons, and I've got 4.5 kilograms. And so, like I said, picked an easy one to get started, but also one that will show you your units. So I'll start with the numbers. Let's see, what is 60 divided by 4.5? And we get 13 1/3. So the number is 13.3. But this will give me a chance to remind you of the units for a Newton are a kilogram meter per second squared. So when I divide by kilograms, I'm going to be left with meters per second squared. And that's perfect. Remember what we did in chapter 1 about unit analysis? Watch your units, follow your units. If they don't come out right, you know you did something wrong. So since I'm looking for acceleration and I know acceleration is measured in meters per second squared, if I don't get meters per second squared, I clearly did something wrong. So obviously, this doesn't prove I did it right, but at least I don't have any indication that I did it wrong. So I'm feeling comfortable about that answer. Also, let me take this as a moment to then point out that notice then there will be times perhaps where they give you the mass in grams and you need to recognize that you better convert it into kilograms before you can continue on with that calculation. Okay, so if that one was fairly straightforward, let's get to a little harder, but still maybe straightforward. Let's try number 5 here. And so number 5 says, in figure 4.7, the net force on the 24 kilogram mower is stated to be 51 newtons. Now, notice again, they said net external force. And maybe I should look at the picture for you. I'm going to click on it. It's going to look at what page I'm on. I'm on page 202. So here is kind of a picture here. So there's somebody pushing a mower. Okay, wasn't too enlightening there. I thought. Yeah, didn't I go 202?
The pages of the book and the pages on the thing line up.
Yes. My bad here. Okay, let me get it a little smaller so I can go faster here. Problems. That is a page. I was just at the top. That's what somebody said, right? I just need a better zoom. I lost it.
Click on the figure to go right to it.
Yeah. Okay, I'm back. Okay, so now let me try this again. Because so you saw the figure. Probably wasn't worth our time to go there. But it says the net external force on a 24 kilogram motor is stated to be 51 newtons. If the force of friction opposing the motion is 24 newtons, what force F in the newtons is the person exerting on the mower? Okay, so this would be a good place to emphasize those first 2 steps. 1, you got a good physical picture of what's going on, and we didn't have to draw it. They showed us. There's a person pushing a mower. So the object is actually a mower. So let me not try to draw a mower too well because I couldn't, but let me do something like that. But once you have a good physical picture, then we can do a free body diagram. And maybe putting the forces then in blue, I would say there is a push from that human, and then there is some friction. And then what we call the net force, I'm going to come back to my diagram here, that net force is what you get when you combine all those forces together. So there's no real vectors involved because we're only doing the x motion. I would say the force from the human then minus the friction is equal to the net force. And the reason for me picking this one is really to get you to kind of see it's really easy to mix these up. To mix up the force from the person with the net force, or the friction from the force of the person, or the friction from the net force. But there's really 3, and maybe I shouldn't say 3 forces, there's 2 forces, and then there's the result of those 2 forces, okay? So we need to be careful here. When they say here, it's stated to be, the net external force is stated to be 51. So the one they're giving me here is 51 newtons. Then it says if the force of friction is opposite of the mower, and it's at 24. So that's opposite why I put the negative here, and then I put the 24. The one that I don't have then is the force from the person pushing the mower. How much force is that one putting on there? And then it says, what is the force in newtons of that person exerting on the mower? So solving this mathematics, moving this over to here, makes 75 newtons. And so hopefully that's kind of making sense. The person pushes with 75 newtons. The friction then is 24. The net force being the difference makes 51. Just have to be careful. Which ones are they giving you? And that's how we get net force. Net force is the combination of all the forces. Now it says, suppose the mower then is moving at 1.5 meters per second when the force F is removed. Now, which one is removed? The human one. Again, it's back to my statement. Careful which force they're talking about. Okay? The one that is removed is the human. So you still have friction. So you still have a net force, is what I'm getting at. How far will the mower go before it comes to a stop? All right. So this helps illustrate my little diagram a little better. In fact, it then gives us a chance to go all the way down to position, because it's saying how far does the mower go. So during the second part of this, I'm going to then say, well, what is the acceleration of this mower? And to do that, I need to know the net force. Now, be careful. The net force is no longer 51, correct? The 51 is what you had when the human was pushing on it with the friction. But now, they said they let it go or something like that here. Suppose that when the force is removed. So somehow the person stops pushing, or they just relax their arms or something. But now they don't push, and so it's just kind of going on its own. It had gotten up to a speed of 1.5 at that moment. But what I would then say here is the net force now is just the friction. Remember, the net force is adding up all the forces, and at this point, there's only one. It's just the negative 24. And so when I divide that by 24 kilograms, I'm going to get, number-wise, a -1. And then the units are the same that we just did in problem number 3. And they'd come out to be meters per second squared. So again, this is the main thing I want to show you in the next 3 chapters. You can see that this could get pretty hard if we're going to spend 3 chapters on it and looking at all the forces. But we look at the individual forces, that gives us net force, and that gives us acceleration. Then we can use that to do the same thing we've been doing in the other problems. And so now that I know the acceleration and I know the initial speed, and they ask how far it goes, all of that makes it sound like a constant acceleration problem, kinematics equation number 2, since they're asking about how far does it go. Oh, actually that might not be a good one to do, because that one involves time, and I don't have that, and they're not looking for it. That makes me think equation 3 might be the better option. So I'll go ahead and use equation 3. Of course, I could have used equation 1 to get time and then put it in equation 2, which is how we got that one in the first place. So choice is kind of ours. But again, this part of the problem goes back to our earlier information. All right, so my initial speed is 1.5 meters per second, and I'll square it. And the key to this problem is indirectly they are telling us the final speed, because it says how far will the mower go before it stops. So they're telling us a final speed of 0. And so then this is 2, and this is -1 meter per second squared. And this I'm just going to write as delta x. That's what they're looking for. How far did it go? And I'll just do these numbers kind of quickly since you've seen these one-dimensional motion already quite a bit. Let me take the 1.5 and square it, and move it over to here so it's negative, cancel with that negative, then divide by a 2, and it looks like it would go about 1 1/8. So the delta x would be 1.125 meters. So there's how far it's gonna go. All right, maybe a little harder one here. Let's try number 9. So number 9 says, suppose 2 children push horizontally, but exactly opposite directions on a third child in a wagon. All right, since they didn't give me a picture for this, I'm going to emphasize my first step and make sure I have a good physical picture of what's going on, because that's really going to help with my free body diagram, which then is going to help with my math and as I solve the problem. And this problem's a little more sophisticated. Oh, I didn't want to erase that. Oh well, maybe I'll redo it. But now we can finally kind of highlight my 4 steps. 1, good physical picture of what's going on. 2, free body diagram. 3, write out the equations and solve the equations. So step 3 and 4 I think are pretty obvious once you get 1 and 2 down. That's why I kept emphasizing 1 and 2. So I'll say it again. Good physical picture, free body diagram, writing out the equations, and then solving it. But of course you can't solve it until you write out the equations. And you can't write out the equations until you get that free body diagram. And the free body diagram is you got to get a good picture. So in the first sentence it looks like we've got 2 children pushing on a third child. So maybe I'm going to put the third one here, and for whatever reason I'm going to make the other 2 children bigger, and they are then pushing. And like I said, just doodle a little picture. It doesn't have to be fancy. Look how terrible mine looks. Okay? But it definitely gives me a chance to think about what object am I focusing on, and what are the forces on that object? Where are they coming from? All right. And the fact that they have opposite direction, I've done the arrowhead. Okay. Now, the first child exerts a force of 75 newtons, and the second one at 90 newtons, comma. Friction is 12 newtons, and the mass of the third child plus the wagon. Oh, and I'm sorry, I forgot to say the third child was in a wagon. Oh, and I should have put that in my picture. Sorry. Skipped right over that. All right. So, wagon. What did we have? We had 1 child pushing at 90. Another pushing at 75. I think there was some friction somewhere. So a second force is 90. Friction is 12. Mass of the child in the wagon is 23. So I'm going to go ahead and say, all right, in my mind, I am focusing on the motion of the child in the wagon. And so the external forces clearly are from the 2 individuals who are pushing on the child and the friction. Now, the friction would be the opposite of the motion. I'm going to go ahead and just assume maybe everything starts at rest, and since this child is pushing harder, it's going to kind of move this way. So I'm going to put, and I forgot now, was it a 12? Yeah. And then the mass was 23. And that's your step one. What's going on in this picture? Okay? And of course, this problem says, go ahead and do this. What is the system of interest if the acceleration of the child in the wagon is to be calculated? So it would be the child and the wagon together. Okay? Not collectively all three children, or the left one or the right child, but collectively. I think I did that. Then it says, draw a free body diagram and include all the forces acting on the system. So that's my step 2, and want to encourage you then that after you get a good physical picture of what's going on, you can then just say, and usually I just keep it real simple. I don't even try to draw a child in a wagon. I just make a little dot and say, all right, what are the forces? Because remember, it doesn't matter where the forces came from. It's just a matter of knowing what they are and what direction they're doing. So I would then put something like this. I would say there is one force that's 90. And again, I don't care where it comes from. That's why I don't put it in the free body diagram. That's how we help our thinking. It doesn't really matter where it came from, a child or an adult or a giant rubber band, whatever is pushing on the child. It's 90. That's all that matters. And there is another force pushing on the child, 75. And again, it doesn't matter whether it comes from a child or adult or something else. It's just, we just need to know that it's 75. We then have a friction of 12. And that might be the harder one because we have to kind of say, okay, what direction is it going to be moving? Because it's going to be opposite the direction it moves. So I'll put that one in there. And so that's step 2. Just what are the forces? Yeah.
Oh, wait. So I'm confused like why the arrows are pointing away if it's pushing. That's just like, is that irrelevant? Or?
You mean away from the person who's pushing?
Yeah.
Because
Like why are they not like on your second diagram? In the first diagram, you're showing pushing.
Oh, I see.
Is that just irrelevant?
Yeah, that's irrelevant. Yes, I see what you're saying. I kind of drew it like it looked like somebody was pulling from this side.
Yeah.
But again, what matters is the magnitude and direction.
So either way is correct.
So either way is correct. Good point. And I like to, without even thinking, I just like to draw the arrowheads away from my object, so I put it over here. But I do see what you're saying, that this drawing here would probably be more representation of what I did here. Yeah. All right. Yeah, but both of these would be the same thing. Again, it's just the magnitude and the direction.
And as long as the friction is opposing the 90 newton force. Right?
So yeah, as long as the force of friction is pointing that way. Mm-hmm.
And we put friction that way because the greater force is 90?
Well, that's where the author could have done a better job, but the friction will always be the direction opposite of where it's moving. Now, that's not always opposite of the largest one, because it could have already been moving, say, in this direction when the child comes up and pushes, so it's moving this way. So, but I think in this problem, I'm going to read into it and say, we're going to start with the child getting in the wagon, and then we're going to have fun. So I'm going to start at 0 speed, which means it will move in the direction of the bigger force, which means the friction will be opposite of the bigger force. Yeah, they could have been more clear, yeah.
I get that the wagon is moving like across the x-axis, but if the friction is going to be the F net for the y, then would it be considered, would you solve it?
Ah,
A little,
excellent. Now, I deliberately, just so I could focus on the motion of the wagon, did not put in that there would be then the weight of the wagon and the ground pushing up on the wagon, a normal force. So when I go to step 3, X and Y, I need to figure out what is the net force in the x direction, as well as what is the net force in the y direction. So I'll start with the easier one, I think. I don't know, maybe the x direction, because I have a 90 and then minus a 75 and minus a 12. So 90 minus 75 minus 12. So 90 minus 75 is what? 15 minus 12 more would make a 3. Was it really a 75? Yeah, 75. Okay. Now, in the y direction, all I know is the normal force is up and the weight is down. I do know that there is no acceleration in the y direction of the wagon. Wagon's moving only accelerating in the x. So I can set that equal to 0 and learn that the normal force is equal to the weight. So the ground pushing up is equal to the weight pushing down. Glad you asked it, but we don't really need to calculate, but I'm going to go ahead and calculate it. The weight is mg, and they did say that the mass is 23 kilograms, and remember g is 9.8. This might be a good chance for me to point out that do not think that the weight is the mass. Okay? And so I take the mass and multiply by 9.8. So 23 times 9.8 gives me 225.4 newtons. And so if they had asked what's the normal force, I can get it by using Newton's second law, knowing from the picture that acceleration is 0, and I got it. And great question, although you made the problem harder than I intended it to be, because I think they're just asking about horizontal, because then C says here, calculate the acceleration. And I'm pretty sure they're talking about the acceleration in the x direction. So the acceleration in the x direction would be the net force in the x divided by the mass, which we just said is 3 newtons, dividing by the mass of 23 kilograms, meaning I would have 3 divided by 23 and coming up with 0.13 meters per second squared. So that would be the acceleration in the x direction. Yeah. Yeah.
So what is the n minus w?
So the n minus w is me looking at the free body diagram and adding up the forces in the verticals.
Oh, okay.
So normal is up and weight is down.
It just, yeah, that's n minus w would just be equal to the f and y. Is that what you're
Yeah.
equivalencies?
Yeah, so net force in the y direction means combine all the forces in the y direction. Mm-hmm. And there's only 2 of them, a normal and a weight. Yeah. And actually, I'm glad you asked about that one, because I did want to show you 2 dimensions before we ran out of time, and we're probably have time to maybe do one more. What would be the acceleration if the friction was then 15? So if I came back up here and said, okay, well, if this was a 15, wouldn't this net force come out to be 0? So what would be the acceleration? 0. Mm-hmm. So see what I mean by that strategy? Combine all the forces together, of course keeping x's with x's and y's with y's. Then you can divide that net force by its mass to get the acceleration, and that's what we're just going to keep doing over and over and over, no matter how many different forces we have and no matter how complex it gets. Newton's second law. And that's why I said here 2 hours ago or 3 hours ago, this is actually from memorization pretty easy stuff. It's a few simple principles that explain the universal phenomenon. Now we just have to look at each problem individually and figure out what forces we have, what direction they are, finding the net force, finding the acceleration, and see how the pieces fit together. All right, so well, that was number 9. Let's try number 16. Uh, 16 says, a brave but inadequate rugby player is being pushed backwards by an opposing player who is exerting a force of 800 newtons on him. All right, well, let me pause at that first sentence. Let me do some doodling. Let me say it again. This is always my step 1. Get a good physical picture of what's going on, because that will help in step 2. What's the free body diagram? And once you have the free body diagram, that will help in step 3, which is to write out the equation. And of course, once you have the equation written out, that'll help you in step 4, which is solve it. All right. So if I understood right, there was 2 rugby players. The first rugby player, so let me call this player 1. This is what they labeled the inadequate rugby player. So a brave but inadequate rugby player is being pushed backwards, so there's a movement backwards, by an opposing player who exerts a force of 800 on him. So let me make player number 2 a little bigger. So here's player 2. Player 2 is now pushing with 800 newtons onto player number 1. Okay, so I think that's what I got going. Now, the mass of the losing player, I'm going to take that as the inadequate player, the one who's losing ground. So the mass of the losing player and their equipment is 90 kilograms, and he has an acceleration of 1.2 meters per second squared backwards. Okay, so I'm going to put underneath 90 kilograms. I'm also going to say there is some acceleration of 1.2 meters per second squared going backwards. So again, just step 1, make sure you got a good understanding of what's going on here. All right, now the questions begin. A, what is the frictional force between the loser's player's feet and the grass? Now, before I get that far, I'm going to ask, what other forces are happening here? So in other words, if player 2 is pushing on player 1, anything else going on? Okay, good. I hear a bunch of them, and you're all right here. Hopefully the one that's obvious then is player 1 is pushing back with 800. Did you catch that? Player 1 is still pushing back with 800, but player 1 is losing ground. So what? What if player 1 is in a yellow jersey? So what? They're equal and opposite, right? If 1 pushes on 2, then 2 pushes on 1, equal and opposite. Don't make this extra hard. It's easy to do because it's easy to say, well, that one's losing ground. Well, wait, I would say they're losing ground because their net force is negative. And that other force is not on player 1. And this is where it begins to get real. Let's keep talking. Because down here at the feet, and maybe I'll match it in green. No, let me go blue. So all the forces on player 1 are in blue. I would say player 1, to keep player 1 from sliding back, they're digging their feet into the grass. And so there is a force, let me just call it F1, on the grass from player number 1. So therefore, there is a force F1 equal and opposite on player number 1 from the grass. And now, when I look at just player number 1, I would say this F1 must be less than 800. That's why they're going back. They're not going back because this is less than 800. They're going back because the force from their feet on the ground, which then equal and opposite on their body, which is pushing it, is less than 800. That's why they're losing ground. They're losing ground because number 2 is pushing them back more than the grass is pushing them forward. It has nothing to do with the equal and opposite. So that's why I wanted to put this one in green, because it's on the grass. But this one in red because it's on player 2. But right next to each other because the third law says they're equal and opposite. Did you get all those? It's going to take 3 chapters for this to sink in. Right? I told you. It's going to get real. And we'll make sure we wrap this up in time, but yeah.
So is F1 the glue one? Is that the friction thing?
You might call it friction as they dig into the ground, yeah.
And then the green one is just, that's like representing him slightly backwards?
Well, I would say they're one and the same. They're equal and opposite. The green one is on the ground. So if this is the cleats in the ground, the green one is the force on the grass, and that's why the grass is getting torn up. But the equal and opposite is on the player's leg, and that's why they have a little pushback. It's just not enough to overcome the bigger player pushing them. And wouldn't the same thing be true for player number 2? Wouldn't player number 2 be digging their feet into the grass? And so they would be pushing on the grass, let me call it F number 2, and put it in green because it's on the grass. But then the equal and opposite in red, F number 2, would be on player number 2. So these are equal and opposite, but they're on different objects. And so the red ones are on player 2, the blue ones are on player 1, the green ones are on the grass. And when I do a free body diagram, I need to pause and ask myself, am I focusing on player 1, player 2, or the grass? Because I only care about the forces on that object, not all 6 of them that are listed there. And that's why we can get overwhelmed if we look at all the forces. We only want to look at the ones on that particular player. And so it says right here, what is the force of friction between the loser player's feet and the grass? So if I look at the losing player, player number 1, I have a force pushing them backwards at 800 and a force that's pushing them forward, which is equal to what's on the grass, and that's the question they're asking. So the net force here, and so this is step 3, do the math. Now that I got the free body diagram, I would have a negative 800, a positive F1. That is the net force. And net force has to equal what? Mass times acceleration. And so the mass is 90 kilograms. The acceleration is a negative 1.2 in my picture. And so I can then get 90 times a negative 1.2. So this is negative 108 newtons. This is then F1. I'll move this over to a plus 800. And so what do I get for F1? 692 newtons. And maybe that helps now. You can see that the amount of force on player 1 from the grass as they dig in their cleats is not overcoming the 80 that is pushed on them from the opposing player. That's why they're getting pushed backwards. And they have a net force of 108. Negative 108, that's why they go backwards. All right, well, we better wrap this up here so the other class can come in here. But B, what force does the winning player exert on the ground to move forward if his mass and his equipment is 110? So this is kind of the same problem, except now my free body diagram is going to be player number 2. And so when I do free body diagram of player number 2, and I'll just make a little dot for player number 2, and I'm going to come over to here and say, okay, what forces are on player number 2? It looks like, again, there would be a force of F2 from the ground and a force of 800 pushing back. That's the action-reaction between the two players. And so when I go to calculate net force, I would go, I guess, 800 positive direction minus F2. That has to equal mass times acceleration. So that's what I mean by step 3. Once you get the free body diagram, then write out the equation. Add up all the forces, set it equal to ma. And in this case, the second player has a mass of 110, and I'm presuming, since they are wrestling together, that the acceleration of each player is the same as they're kind of moving on backwards. And so F2 becomes this 800, and then I'll move this over to here, plus 110 times 1.2, and so 932 newtons is the force that the grass is putting on player 2 as it digs in their feet. And now hopefully that makes sense. The force pushing player 2 forward is more than the force pushing the player back. Or, depending on what you call positive and negative. I probably should have drawn them the other way around. I drew them so they moved in the negative direction, so that might have been your question. And then I think I did C. Draw and sketch the situation showing the system of interest and solve each part. For each situation, draw the free body diagram and write out the net force. And so I'll end today's lecture with saying, did you see what I did? 4 steps. 1, good physical picture of what's going on, which includes which forces are on which objects. So then step 2, I can draw the free body diagram. Or in this case, I would say free body diagrams, because one time they asked about player 1 and another time they asked about player 2. So I wanted to draw the free body diagram for each separate player. This is where you can make it too hard on yourself by worrying about all the other forces. You only want to worry about the forces on that object. And that's why it's so important to have step 1, a good physical picture, so you can draw step 2, the free body diagram. Finally, step 3, write out the equation. And what I mean by that is add up all the forces and set it equal to ma. That's Newton's second law. And then finally, step 4 is solve it. And so hopefully those last 2 are obvious once you get through the hard part, which is recognizing the forces. All right, well, we'll have to stop there for today and keep working on this. All right.